The electrical forces of cardiac depolarization and repolarization are vectors. And as vectors, they obey certain mathematical principles. You need to have a basic knowledge of some of these principles in order to understand the ECG abnormalities discussed in this section. Just take a few minutes to watch this video before moving on. Firstly, vectors have both magnitude and direction. In mathematics, a vector is drawn as an arrow indicating its direction, while the length of the arrow from the initial point to the terminal point is indicative of magnitude. If the vector shown here represents a depolarizing voltage of 1 millivolt traveling in the direction indicated, then a depolarizing force of 2 millivolts traveling in the same direction is represented by an arrow twice its length. We've already seen that if this 1 millivolt depolarizing vector is moving directly towards an ECG lead set at a standard sensitivity, it will produce a positive deflection of 10 small squares on the readout from this lead. In contrast, in a lead positioned such that the vector is heading directly away from its direction, it will produce a negative deflection of the same magnitude. This is simple enough. However, it is important to realize that vectors can be resolved into smaller components, traveling in different directions. Components are also vectors and may be drawn in many different directions off the initial point of the parent vector, in accordance with the so-called parallelogram rule. As illustrated here, the magnitude of components are linked by the requirement that they form the sides of a parallelogram touching the apex of the parent vector. For our purposes, this means that a depolarizing vector produces an effect in leads positioned off its direct line of travel. Calculation of the magnitude of this effect in the direction of any given lead is relatively straightforward. Consider the situation shown here. A depolarizing vector of voltage V is traveling at an angle theta off the direct line to lead A. What is the maximum voltage component of this vector traveling directly towards the lead? To calculate this, we let the direct line to the lead define the x-axis. Using the parallelogram rule, if we draw the parallelogram as a rectangle, this sets the component on the y-axis at 0 relative to the lead. The reason for this will be obvious shortly, and gives us the maximum possible length of the component vector traveling directly towards the lead. The magnitude of this x-axial component can be calculated very simply. In a right-angled triangle, the cosine of the angle theta is given by the length of the adjacent side divided by the length of the hypotenuse. Remembering that length equates to magnitude, the magnitude of the x-axial component is therefore equal to the magnitude of the parent vector multiplied by the cosine of the angle theta. In the example shown here, a depolarizing force of 1 millivolt is traveling at an angle of 40 degrees off the direct line to the lead. The component traveling towards the lead is therefore 1 multiplied by the cosine of 40 degrees, or 0.766 millivolts. At standard ECG sensitivity, this gives a positive deflection of just under 8 small squares in the readout from the lead. Remember also that cosine declines as the angle increases. Therefore, the larger the angle the parent vector makes with the direct line to the lead, the smaller the component in its direction. Importantly, as the cosine of 90 degrees is 0, when the parent vector reaches 90 degrees relative to the lead, the component on the x-axis will also be 0, and no deflection is produced in the readout. This is important. A vector has no component at right angles to itself. So no matter how large in voltage a depolarization vector may be, if it is moving at 90 degrees relative to an ECG lead, no net deflection is produced in the readout from that lead. Once the vector's direction of travel moves beyond 90 degrees relative to the lead, the signal produced is negative. And the same simple maths we've just employed can be used to calculate the magnitude of the negative signal generated.